Dear students, now I want to discuss dipole moment. So this is very important concept from chemical bonding and molecular structure. So dipole moment mu equal to d into E. E means charge per unit volume. D means distance between two adjacent atoms or distance between two opposite charges. Adjacent to opposite charges. So this is important formula mu equal to d into E. Okay. Now CGS unit for dipole moment. Dipole moment. Mu equal to formula d into E. Distance between two atoms, suppose AB one molecule, distance d 1 angstrom, you can assume 1 angstrom, and charge per unit volume 4.8 into 10 to the power of minus 10 ESU. Okay, yes. So 1 angstrom 10 to the power of minus 8 centimeters into 4.8 into 10 to the power of minus 10 ESU, electrostatic unit. Okay, per unit volume charge you can take in ESU 4.8 into 10 to the power of minus 10 ESU. So now 4.8 into 10 to the power of minus 18 ESU centimeter. Now 4.8. So this value, for this value we can use debye. 1 debye equal to 1.0 into 10 to the power of minus 18 ESU centimeter. This is 1 debye. 1 debye equal to 1.0 into 10 to the power of minus 18 ESU centimeter. So 4.8 debye. Debye is CGS unit. Now SI unit or MKS unit for dipole moment. MKS or SI unit for dipole moment. MKS or SI unit for dipole moment. So mu equal to d into E. Now distance you can take 1 angstrom 10 power minus 10 meter into charge per unit volume for SI or MKS unit 1.6 into 10 to the power of minus 19 coulomb. So now 1.6 into 10 to the power of minus 29 coulombic meter. Understood? So this is SI unit relation. Understood? Now relation between debye and coulombic meter. Relation between debye and coulombic meter. Okay, coulombic meter. So 4.8 debye equal to 1.6 into 10 to the power of minus 29 coulombic meter. 1 debye equal to 1.6 by 4.8 into 10 to the power of minus 29 coulombic meter. It is not centimeter, coulombic meter. 1 debye equal to 16 3 is 48, 1 by 3, 0.333 into 10 to the power of 29 coulombic meter. 1 debye equal to 3.33 into 10 to the power of minus 30 coulombic meter. This is relation between debye and coulombic meter. Debye and coulombic meter. Understood? 1 debye equal to 3.33 into 10 to the power of minus 30 coulombic meter. Clear? So now relation 1 debye equal to 1.0 into 10 to the power of minus 18 ESU centimeter, that is equal to 3.33 into 10 to the power of minus 30 coulombic meter. Clear? So this is the very important relation for NEET or JEE. Clear? Now, percentage ionic character, how can you calculate? Understood? Percentage ionic character, how can we calculate? Important formula. Important formula. Important formula. Percentage ionic character. Percentage ionic character is equal to mu observed by mu calculated into 100. This is very important formula. Mu observed by mu calculated into 100. Very important formula. Percentage ionic character is equal to mu observed by mu calculated into 100. Now, I want to discuss one problem. One problem. The observed dipole moment. The observed dipole moment of HCl is 1.03 debye if the bond length of HCl is, its single bond Cl is 1.275 angstrom, then percentage ionic character is, this is the question. The observed dipole moment of HCl is 1.03 debye. If the bond length of HCl is 1.275 angstrom, then percentage ionic character is. So now, solution. Mu observed already given. What is the value? 1.03 debye. Mu observed already given. Now, mu calculated equal to D into E. Debye, that is a CGS unit. Distance between two atoms 1.275 angstrom given, and CGS unit in ESU 4.8 into 10 to the power of minus 10 ESU, electrostatic unit. Now 1.275, 1 angstrom 10 to the power of minus 8 centimeters. 4.8 into 10 to the power of minus 10 ESU. Now 1.275 into 4.8, if you multiply, you will get 6.18 into 10 to the power of minus 18 ESU centimeter. 10 to the power of minus 18 ESU centimeter, that is equal to 1 debye. So 6.18 debye. Understood? Debye. Now, observed dipole moment in debye calculated, already we have calculated in debye, 6.12 debye. Now, percentage ionic character equal to mu observed by mu calculated into 100. Mu observed by mu calculated into 100. So, mu observed value how much? 1.03 debye. Mu calculated how much? So, mu observed 1.03 debye. Mu calculated 6.18 debye into 100 If you simplify, you will get 16.8% is the right answer. Okay, 16.8% is the right answer. I hope everyone understood this one. Yes. Now coming to applications of dipole momentum. Applications of dipole momentum. Okay, applications of dipole momentum. Now first application, diatomic molecules. Okay, diatomic molecules. If different electronegativity increases, then bond polarity increases. If bond polarity increases, then dipole moment also increases. Dipole moment also increases. If different electronegativity increases, then bond polarity increases. Bond polarity increases. Bond polarity increases. Therefore dipole moment increases. Therefore dipole moment increases. Okay, therefore dipole moment increases. So dipole moment mu. Here hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. Clear? So hydrogen electronegativity 2.1, fluorine 4.0. Hydrogen electronegativity we know very well 2.1. Fluorine 4, chlorine 3, bromine 2.8, iodine 2.5. Understood? Now different electronegativity. So this is 1.9. Different electronegativity 0.9. Different electronegativity 0.7. Different electronegativity delta En. Different electronegativity 0.4. Sorry. Different electronegativity increases, then bond polarity increases. Okay, different electronegativity increases, then bond polarity increases. Bond polarity increases, partially negative, partially positive, like partially negative, more electronegative atom, less electronegative atom, partially positive, like partially negative, partially positive, partially negative, partially positive. So different electronegativity increases, then bond polarity increases, then dipole moment increases. Okay, among the four molecules, which molecule having greater dipole moment to greater bond polarity? Hydrogen fluoride molecule. So hydrogen fluoride greater than hydrogen chloride, greater than hydrogen bromide, greater than hydrogen iodide. This is the first important application. Understood everyone? Now second application, for symmetrical molecules. For symmetrical molecules, dipole moment 0, mu value 0. Mu value 0 means, you know, non-polar molecule. Non-polar molecule. Okay, for symmetrical molecules dipole moment 0. Dipole moment 0 means non-polar. Finally, total molecule will become non-polar. Clear? Yes. Even though polar bonds present in a molecule, but resulting dipole moment is 0, then it is simply known as non-polar. Okay. Example: carbon dioxide. Carbon dioxide. Here, its shape is required. What is the shape of carbon dioxide? Linear shape. You know here, CO bond, polar bond, CO bond, polar bond. Bond polarity pointing towards oxygen, because oxygen more electronegative, carbon less electronegative. Here two bond polarities are there, two bond polarities working towards oxygen. It is linear. What is this? Linear. Linear. You know, 180-degree bond angle, linear. 180-degree bond angle, linear shape. Understood? So, two bond polarities are there, but they are working in opposite direction. That's why resulting dipole moment is 0. Okay? CO2 molecule has two C double bond O polar bonds. C double bond O polar bonds. Understood? But both C double bond O polar bonds cancelled with each other. Cancelled with each other. Okay. Therefore, resulting dipole moment. Therefore, resulting dipole moment. Okay, resulting dipole moment is 0. Resulting dipole moment is 0. Is equal to 0. So mu value 0. Mu value 0 means non-polar molecule. Non-polar molecule. Understood? Very, very important. Mu value 0 means non-polar molecule. So very, very important application. Even though polar bonds, but final molecule non-polar. Coming to example 2. Example 2. Example 2, boron fluoride. Boron trifluoride, BF3. Boron trifluoride. What is the shape of the molecule? Trigonal planar shape. What is the shape of the molecule? Trigonal planar shape. Trigonal planar shape. Trigonal planar shape. Trigonal planar shape. So bond polarity. Bond polarity. Bond polarity working like. So now these two resulting bond polarities working like. So this one bond polarity, resulting bond polarity working in this direction. Understood? So now here this one and this one both cancelled out. Understood or not? Now coming to here, these two resulting dipole moment is working like, means these two polar bonds resulting dipole. Now this one cancelled out. Similarly, resulting dipole moment this one and this one cancelled out. That's why resulting dipole moment 0. Resulting dipole moment 0. Okay, resulting dipole moment 0. Resulting dipole moment 0 means it is non-polar molecule. Okay, non-polar molecule. Resulting dipole moment 0 means non-polar molecule. Understood everyone? Yes. Now coming to third example. Example 3. So coming to example 3, methane. Methane, CH4. It is a tetrahedron symmetrical molecule. So we are unable to explain on paper plane or board plane. So it is a tetrahedron molecule, symmetrical tetrahedron molecule. Symmetrical tetrahedral molecule. Symmetrical tetrahedral molecule. Symmetrical tetrahedral molecule. Therefore, dipole moment 0. So dipole moment 0 means resulting molecule, resulting polarity 0. Na? That's why non-polar molecule. Mu value 0 means non-polar. Understood? Mu value 0 means non-polar molecule. Understood? Similarly, all tetrahedron symmetrical molecules, all, not only methane, all tetrahedron symmetrical molecules, tetrahedral symmetrical molecules, for them dipole moment 0. Okay. Similarly, carbon tetrachloride, carbon tetrabromide, okay, silicon tetrachloride, silicon tetrabromide, okay, etc. Okay, for them dipole moment 0. For them dipole moment 0. Understood? For them dipole moment 0. Clear everyone? So this is one important application. Clear? Now coming to here another molecule also, another example also we can take. Example 4. Example 4 PCl5, phosphorus pentachloride, PCl5. Now phosphorus pentachloride, PCl5. Its shape is trigonal bipyramidal. Its shape is trigonal bipyramidal. You know, three equatorial, this is equatorial, equatorial. So like boron trifluoride, okay, resulting dipole moment 0 for them, for three trigonal corners like boron trifluoride, here 0. Now remaining two axial, exactly 180-degree bond angle, axial. So these two axial bonds, bond polarity is cancelled, axial. So that's why resulting dipole moment 0. Mu value 0 means that is non-polar molecule. Mu value 0 means non-polar molecule. So what is the shape? Trigonal bipyramidal. Okay. So it's a dipole moment 0, non-polar molecule. Now coming to next example. Example 5, SF6. Here also 6 polar bonds are there. How many polar bonds? 6 polar bonds. But resulting dipole moment 0. So this is exactly 180 degrees opposite. cancelled. These opposite 180 degrees cancelled. Now above, below, exactly 180 degree cancelled. So this is octahedral shape. What is this? Octahedral shape. Understood? Octahedral shape. So now octahedral shape. Mu value 0, non-polar. Mu value 0, non-polar. SF6, mu value 0, non-polar. Understood or not? All dipoles are cancelled out. Clear? Now coming to third application. Now here just observe diatomic molecules, one application done. Next, for symmetrical molecules mu value 0, how many examples done? 1, 2, 3, 4, 5 examples done. Now coming to third application. Asymmetrical molecules. You can take asymmetrical molecules. So asymmetrical molecules. Example 1, water. What is the shape? Bent shape. What is the shape? Bent shape. Or V shape or angular shape. Now two bond pairs, two lone pairs. OH, oxygen more electronegative. Bond polarity pointing towards oxygen. Two lone pairs resulting bond polarity working like. Here bond pair polarities, lone pair polarity working in same direction, top side. So all polarities are working in same direction, means top side means it has greater resultant dipole. Understood? So dipole here, all dipoles, their polarities working in same direction means mu not equal to 0. Mu not equal to 0 means it is polar molecule. You know, bond angle 104 degree 30 minutes. Understood? Now coming to next example. So this is very important application. Example 2, very important. So example 2, that is very important. That is ammonia and NF3. Ammonia and NF3. Usually, which has greater dipole moment, ammonia or NF3? Generally, we can think, or we thought NF3 greater dipole moment, but that is wrong. NH3 greater dipole moment. Normally, how can we think? Fluorine more electronegative, maybe greater bond polarity, maybe greater dipole moment. Wrong. Among the two, NH3, NF3, which has greater dipole moment, ammonia. Now, NH3, here both have pyramidal shape. Why? You know, 3 bond pairs, 1 lone pair. 3 bond pairs, 1 lone pair. Clear? 3 bond pairs, 1 lone pair. NH bond polarity working towards nitrogen. Nitrogen more electronegative. Okay, and this lone pair working towards top side. Now in ammonia, all bond polarities working in same direction, one direction. That's why resulting dipole moment is greater. Okay. Okay, in ammonia, all dipoles, their polarity is working in same direction. That's why greater dipole moment, mu not equal to 0, but greater dipole moment. Greater dipole moment. Greater dipole moment. Coming to NF3, nitrogen fluorine, which is more electronegative, fluorine. So that's why bond polarity is working towards fluorine, but lone pair always out of the plane. Now here bond polarity is working downside, lone pair polarity working upside, top side. So that's why somewhat bond polarity is cancelled out. But bond pair polarity strength, lone pair polarity strength different. That's why not exactly cancelled. Lone pair polarity working top side, bond pairs polarity working bottom side. So anyhow, not exactly cancelled, not exactly cancelled. So mu not equal to 0. So not equal to 0 means it has some dipole moment polar, but anyhow less dipole moment. Okay, as compared to ammonia, NF3 dipole moment less. Understood? So therefore, here very important, ammonia NF3, which has greater dipole moment to ammonia. Ammonia, its dipole moment is greater than NF3. Okay, ammonia, its dipole moment is greater than NF3. So very important application it is. Very important application. Understood? Yes. Now coming to next application. Fourth application. 1,4 dihydroxyl benzene, 1,4 dihydroxyl benzene and 1,4 dicyanobenzene. Okay, 1,4 dihydroxyl benzene, 1,4 dicyanobenzene. Very important application it is. 1,4 dihydroxyl benzene. You know, this is bent shape. Oxygen, two bond pairs, two lone pairs, bent shape. Two bond pairs, two lone pairs, bent shape. Okay, so very important application. CO bond polarity, working towards oxygen, working towards oxygen. Lone pair bond polarity, two lone pairs resulting polarity like here OH bond polarity, CO bond polarity, resulting bond polarity direction. So anyhow, here resulting bond polarity, here resulting bond polarity, here just observe resulting bond polarity working like, resulting bond polarity working like, okay, anyhow dipoles not cancelled. Okay, resulting dipoles not cancelled. That's why here mu not equal to 0. Mu not equal to 0 means polar. Understood? 1,4 dihydroxyl benzene, it has some dipole momentum, means mu not equal to 0 means it has some dipole momentum, so it is polar. Now coming to 1,4 dicyanobenzene, very important application, so many times asking for NEET JEE me. 1,4 dicyanobenzene, opposite positions, 1/4 para. So now linear, cyanide linear, here bond polarity pointing towards nitrogen, pointing towards nitrogen. So here two bond polarities exactly working in opposite direction, that's why mu value 0. Mu value 0 means that is non-polar. Okay, what is this molecule? Non-polar. So this is Very, very important application it is. 1,4-dihydroxyl benzene mu not equal to 0. 1,4-dicyano-benzene mu equal to 0. Understood everyone? Yes. Now coming to fifth application. Fifth application. Fifth application, ortho dichlorobenzene meta dichlorobenzene and para dichlorobenzene ortho dichlorobenzene meta dichlorobenzene para dichlorobenzene. Clear? So now, for example, suppose here para is greater than meta is greater than ortho. Coming to para dichlorobenzene, you know CC bond is polar bond. Chlorine more electronegative than carbon. So two bond polarities exactly opposite to each other, bond polarity is cancelled, so dipole moment 0. It is para isomer, so mu value 0. Mu value 0 means non-polar. Mu value 0 means non-polar. Understood or not? Now it is greater than meta. So here dipole somewhat not exactly cancelled, resulting dipole moment working like. So anyhow, meta isomer, it has some dipole moment, mu not equal to 0. So polar. Now coming to ortho dichlorobenzene. Here resulting dipole moment very high. Resulting dipole moment is very high. So mu not equal to 0, polar. So here, just wait here, which has greater dipole moment? Ortho isomer greater dipole moment than meta, which is greater dipole moment than para. So ortho highest dipole moment, para least 0. So this is very, very important application. Clear? Now, so para here completely 0. Understood or not? Para completely 0. Para dichlorobenzene mu value 0, purely non-polar molecule it is. Now coming to sixth application. So this is also very, very important application. PCl3F2. PCl2F3. So both have trigonal bipyramidal shape. Understood? Both have trigonal bipyramidal shape, but among the two molecules, one is polar, another one non-polar. Which is polar, which is non-polar? Now observe PCl3F2. Here chlorine, fluorine, 3 chlorine, 2 fluorine, total 5. Around the central atom 5 bond pairs means trigonal bipyramidal. 3 equatorial, 2 axial. Okay. So chlorine, fluorine, which is big size chlorine? According to Vesper theory, valence shell electron pair repulsion theory, big size atoms or bulky atoms or lone pairs particularly occupy equatorial positions to minimize repulsive forces. Okay. For getting perfect structure, perfect adjustment, big size atoms to lone pairs occupying equatorial positions. When big size atoms are lone pairs occupying equatorial positions, then they are experiencing less repulsive forces. Reason: bond angle 120°. More bond angle, less repulsive forces. Less repulsive forces means more existence. So chlorine atoms, big size atoms. That's why preferably that big size chlorine atoms, we can write in equatorial positions. Of course, three big size chlorine atoms are there. We can write in equatorial positions. Understood? Of course, all are equal bond polarity strengths. Why? All are PCl bonds. All are PCl bonds. Understood or not? All are PCl bonds. Equal bond polarities. That's why this trigonal planar cancelled. So now above remaining two smaller atoms, fluorine top side axial, bottom side axial. So these two also exactly cancelled. That's why mu value 0 means it is non-polar molecule. Non-polar molecule. So PCl3F2 non-polar molecule. Now coming to PCl2F3. Here phosphorus. How many big size atoms? Two big size atoms. So two big size atoms preferably occupying which positions? Equatorial. Now, so two chlorine atoms over. Now coming to remaining fluorine atoms. Fluorine, this one. But which has greater bond polarity as compared to PCl bonds? PF bond greater bond polarity, because PF electronegativity difference more, because fluorine more electronegative atom than chlorine. That's why here trigonal planar shape means corners. Trigonal, three corners, three atoms are different. That's why bond polarity is not exactly cancelled out. Of course, remaining two fluorine atoms above, okay, above and below. So these are cancelled. Above, below, these are cancelled. Above, below, these are cancelled. But in trigonal position is there now. This trigonal position, these are not cancelled because fluorine, chlorine, their electronegativity is different, their bond polarity strength is different. Axial, above, below cancelled, no doubt at all. Axial, above, below cancelled. But equatorial bond polarity is different. That's why here mu not equal to 0. Mu not equal to 0 means polar. So PCl to F3 polar. PCl3 F2 non-polar. Very, very important application. Understood? Yes. Coming to last application. Okay. Cis alkene. Cis 1,2 difluoroethene and trans 1,2 difluoroethene. Cis 1,2 difluoroethene, trans 1,2 difluoroethene. Okay, so now cisalkene, transalkene. Cis means same side attachment. Either two hydrogens or fluorine atoms same side of the double bond. Two fluorine atoms or two hydrogen atoms opposite side of the double bond, trans. This is the cisalkene. This is the transalkene. Okay, clear? So now coming to cisalkene. Cisalkene bond polarity. pointing towards fluorine. So resulting dipole moment working like resulting dipole moment. That's why mu not equal to 0 means polar. This is polar molecule. Now coming to here, this is bond polarity. This is bond polarity. Both bond polarities exactly cancelled out. Exactly cancelled out. So mu equal to 0. Mu equal to 0 means that is non-polar molecule. Non-polar molecule. Mu equal to 0 means non-polar molecule. So cis, it is polar. Mu not equal to 0. Trans, mu equal to 0, that is non-polar molecule. Clear? So very very important concept it is. Okay. So today we have learned dipole momentum and CGS units, SI units, and we learned relation between Debye and Debye and Debye and Coulombic matter relation we have learned, and we have completed one problem also, percentage ionic character. Percentage ionic character equal to mu observed by mu calculated, one problem also we have done, and applications, 7 applications we have learned. Clear? So this is useful concept, very very important for NEET JEE. Thank you so much. JEE advanced also, this is important concept. Thank you so much.